So I don't know, we are in the middle of discussing about air movement, which we usually call weather, right? So although very well-educated people, I realize sometimes people are kind of confused about the weather and climate. So we will, before we dive into today's discussion topic, let's take a look at the difference between weather and climate. How many of you can tell the difference between weather and climate, you think? One? Just one? What's the difference between weather and climate? Okay, I can see the few hands. Yep.
Weather is on a day-to-day basis, and climate is over a long period of time.
Is there any? Yep.
In one area.
I like the answer. Anybody has a different opinion? Go for it.
Well, it's similar, but I always remember is climate is what you expect, weather is what you get.
Say that again.
Climate is what you expect, like throughout the day or throughout the year, and weather is what you get, what actually happens each day.
So you think climate is more like prediction,
Yeah,
and then weather is kind of what it is actually happening.
whatever in that area, the average thing that happens during that time of year.
Let's take a look at a few video actually to help your understanding. Let's start from here. This is the news coverage early this year, kind of introducing the weather statistics of year 2012. Let's take a look. Voice. Hold on.
Natural disasters cost a total of $160 billion around the world in all of 2012. Sandy, of course, was a big part of that cost here in the East, and it's still costing. In the Midwest, it was the drought. These new numbers coincide with a new official look at just how hot our past year was. And our report tonight on this from our Chief Environmental Affairs correspondent, Ann Thompson.
Raging infernos, surging seas, howling winds. 2012 was a year of extreme weather and one for the history books. Hotter than any year on record. The result, federal scientists say, of nature and man-made climate change.
The 2012 temperatures are part of a long-term warming trend, and that is associated with climate change. It is hard to pinpoint what percentage climate change had of a role in the 2012 temperatures. It did have a role.
Under normal conditions, we should see one record high for every record low. But in the first decade of this century, we saw 2 record highs for each record low. In 2011, it was 3-to-1. And last year, 5 record highs for each low. In 2012, much of the country sweltered.
1 out of every 3 Americans had at least 10 days where they had to deal with temperatures at or above 100 degrees. That's a lot of heat.
All that heat, plus a lack of rain and snowfall, created a historic drought that still grips over half the country today, making the Mississippi River less than mighty. So shallow in places, barge traffic could come to a halt.
I think that we're looking at some very risky situations for the middle of the country for the coming year. The persistence of the drought so far is a real concern.
Extreme weather caused extreme hardship. 11 disasters topping $1 billion in losses. 125 people killed in Superstorm Sandy alone. It's not just the U.S. Catastrophic wildfires raged across Southeast Australia this week, fueled by triple-digit heat that forced the government to add a new color to its maps, purple, indicating up to 122 degrees. Back in this country, the city of Chicago, normally snow-covered in January, today tied the record for the most days without at least 1 inch of snow, 319.
Now, the reason this record of 2012 is significant is because what it signals for our future. Federal scientists say we can expect warmer years to become more frequent, with more and bigger intense heat waves and perhaps more drought fire.
Not the last thing we needed to hear, but it's news because of that. Ann Thompson, thank you, as all.
So basically what this news coverage is saying is that you expect in normal condition, equal number of the record high and record low. But if you just do some statistical approach, because of the global warming, which is caused by some natural cause and then significant fraction of the human cause, the daily day variation, if you take a look at the statistical approach for the daily day-to-day temperature variation, you see more hot weather than the cold weather. So basically, climate is kind of a compilation of the weather, day-to-day weather system. So, a lot of times people actually make some mistake this concept that if you live in Alaska, place like that, once you have a very cold day, people tend to say global warming is hoax, things like that. But that's not quite right approach. But let's take a look at this. How many of you know Jon Stewart? Jon Stewart? Yeah, it's kind of funny, guys. You know, kind of sarcastic kind of comedy thing. So early this year in New York City, it got very cold. Then here's this clip here.
An associate professor of aeronautics and astronautics at MIT University, specializing in human interaction with autonomous vehicle systems, and instructs the U.S. Navy on that very subject. Also, possesses the largest cute name to serious job gap, perhaps in our nation's history. But before we get started, I want to thank our audience. Truly, braving perilous weather conditions. It's unbelievable. I'm going to give you a sense. This is how I got to work this morning. Yeah. Driving New York City. Colder than a Richard City. It's New York. I'll tell you, it made me realize something. Global warming is a total hoax. And I'll tell you how I know. Because it's cold today where I live. That's in fact, if anything, there's a new ice age coming today where I live, which we're totally unprepared for because it's been so unseasonably warm this winter. You gotta wonder who's perpetrating this global warming hoax. I mean, climate scientists would be dumb to pull something like that up.
You want to watch this sitting all the way, or? Okay. I can wait 1 more minute.
Pulling off a hoax. This magnitude, perhaps noted Manti Teo prankster. Stop it! With this cold! Our lips are turning blue. We'll catch the blue. Because I have kind of a weak immune system because I'm a Jew. I'm going to be sorry to see this guy go, quite frankly.
All right, so now you can tell the differences between weather and climate, right? So right now we are talking about weather system, how weather system affects on the air pollution, things like that, how air movement is going to transport the air pollution from one place to the other places. And then in terms of climate, which is collection of day-to-day variation of the weather, we will discuss about climate later of this course. That's going to be our last topic for the discussion. So we watch this thing. So let's discuss about a little bit of boring stuff about air motion. So we discussed about the air motion, horizontal air motion so far. And then today we will talk about vertical air motion and then how that affects on the air pollution transport and then how that can actually make it better or worse air pollution in one region, okay? So when you have a parcel of air, and then that if you bring that parcel of air to higher altitude, let's say 1 kilometer above from one point to the other point, and then let's assume that's completely dry, the temperature of air is going to drop about 10 degrees Celsius. Okay? If you are really interested in chemistry, thermodynamics, things like that, you can actually solve this number by equation, but I'm going to skip that. Probably most of you is not that interested in those kind of things. So what you need to remember is that if you bring air parcel from one place to 1 kilometer above, the air temperature is going to be decreasing 10 degrees Celsius. Importantly, is dry air. Where's a dry air thing? Dry. So it's dry air. Unsaturated air by means that completely dry air, there's no water vapor there. Okay, 10 degrees Celsius. What if it's completely saturated? Then temperature decrease is going to be only 6 degrees Celsius. Why is that? Because when we discuss about gas, liquid, and solid, right? In terms of energy, so that's more higher energy side, right? If you want to make solid ice cube into liquid water, then it's all evaporated. What you want to do, you just heat it up, right? By definition, so heat is energy. So you put some energy in the ice cube, it will become a liquid, and then it will become water vapor in the air, right? So as temperature is decreased, some of the water vapor, because it's completely saturated air, then some of the water vapor will condense and then become liquid water, right? So it will basically absorb, it will actually emit some of the energy to the air right here. So temperature decrease, supposed to be 10 degrees Celsius if it is dry, but some energy from these condensing processes actually emit some energy to the air parcel. So temperature decrease is going to be only 6 degrees Celsius. Okay? So it is somewhere between 10 to 6, depends on the relative humidity in the air parcel, right? So these are two factors you need to remember. So let's discuss about it. What's the consequences of the temperature decreases? So let's assume a balloon with the that has bunch of air pollutants. So on the surface, the temperature is equilibrated with the surrounding air to 20 degrees Celsius. And then let's assume also it is completely dry. So your lapse rate is going to be 10 degrees Celsius as you move the air parcel 1 kilometer above, right? So, and then let's assume in 1 kilometer above, there's 3 conditions there. One is 5 degrees Celsius, then 13C, and then 10C, all right? So then let's bring this air parcel to 1 kilometer altitude. Then because it is dry, the temperature is going to be 10 degrees Celsius, 10 degrees Celsius, and 10 degrees Celsius, right? And that depends on the surrounding air temperature. For example, here, if it is 5 degrees Celsius, what's going to happen is that because temperature of this balloon, the air inside the balloon, is 5 degrees C higher than surrounding, so the air is going to be lighter, right? So it's going to be keep rising, right? And then here, if surrounding air temperature is 13C, because this is lower than surrounding, the air balloon, the air inside the balloon is going to be heavier, right? So it's going to be sinking, right? And then if it is exactly the same, we call it neutral, right? So what's the consequences of this unstable, what they call it unstable condition, which is basically surrounding is lower than this air balloon. Then if we assume this is the parcel of air that contains air pollutants, right? Then it's going to be keep rising to the atmosphere then mixing will be going on, right? So in unstable atmosphere, mixing is very active in terms of vertical mixing. So you expect a lower air pollutants concentration in this condition, right? Clear? So in stable condition, then basically your air pollutants on the surface trapped in the the surface of the air, so concentration gets much higher, right? Basically your container of the air pollutants is smaller than unstable condition, right? So neutral is somewhere in between, so,
Okay, wait.
right?
So for stable, the air outside is cooler than inside, so the balloon, no. Is it unstable at the air outside? No. Okay, it's stable where the air outside is cooler than the balloon, so the balloon drops, right?
So in terms of stable condition, yes.
Okay, and then unstable, the air outside is warmer, so the balloon keeps rising, right?
So
No.
5 is bigger than 10 or 10 is bigger than 5?
10 is bigger than 5.
Yeah, so probably that's the answer, I guess, right? So hotter air is light or cooler air is light? Cooler air is lighter. So, okay, let's go back to basic equation. This is constant, right? Because pressure is determined by the altitude, right? So same altitude, pressure is same. Let's assume same volume, right? This is by definition constant, right? Higher temperature means less number of air, right? Air molecule. That means high temperature means light or heavy. You expect the, it gets light, have a more molecule or less molecule? Less molecule. Is that right?
Yeah.
Yep. So high temperature means you have lighter air, right? Low temperature means you have heavier air. Yep.
So why on that picture does it have an arrow going up if the inside of the balloon is colder than the outside?
Which one? Which arrow you are talking about?
Unstable?
On the table,
Here?
unstable, if it's going up,
Yeah.
you said the air in the balloon is lighter when it's, okay, I'm sorry.
Yep. It's very confusing. It's very confusing. I understand. Clear? Yeah. You have 5 more weeks to struggle with this thing. So let's make it a little more complicated. Sorry about that. So here, temperature and altitude, right? So this is temperature distribution. To apply this concept to actual condition, we need to do little math, right? So usually this is how temperature distribution looks like in the ambient condition, real condition, okay? So usually there's a layer in between the higher altitude and then surface, the temperature is actually increasing. We call it inversion layer. So let's chop out 3 different layers. Here, right? And here, and here. And then we are going to define one term called temperature lapse rate, which is there's a negative sign here, and then change of the temperature divided by change of altitude. All right? So let's take a look at the top layer, basically from here, 4 kilometer to 2 kilometer. So the altitude differences from 4 kilometer to 2 kilometer is 2, right? Right there. And then temperature change over the 2 kilometer it's -5 to -20, right? So this is, you ended up having 20.5 degrees Celsius per kilometer. So this is by definition, if you're going up to this layer, if you're going up to 1 kilometer, you expect temperature decrease about 12.5 degrees Celsius, right? So this layer right here, right? Here, temperature is actually increasing, right? So in this layer, it's 1 kilometer of a layer, so 2 minus 1. So if you read the y-axis, there's a 2 and then there's 1, right? And then let's read the x-axis. The temperature at 2 kilometer altitude is 20, and then 1 kilometer altitude 15, right? So you ended up having -5. But because there's minus sign here, although there's minus lapse rate, you have the temperature in this layer actually increasing, right? So basically negative value means temperature is increasing, and then positive value means temperature is decreasing as you go higher, right? So bottom layer, same thing. So from 0 to 1 kilometer, 6 degrees Celsius. The rate of 6 degrees Celsius of the temperature lapse rate is in the bottom layer, right? So 12.5, 5, -5, and 6 in this temperature distribution. Okay? Okay, this is the highlight of today's lecture. So, let's go one by one. It's not really as complicated as you think, actually. So what's the temperature decrease for dry air? It's 10, right? And then saturated air? Yes. So, this red dotted line, let's read here. In 1 kilometer altitude is 10 degrees Celsius, right? Up there in 2 kilometer is 0 degrees Celsius, right? So this is basically expression of dry lapse rate, temperature decrease for dry air, right? Yeah, basically this thing, right? I just bring 2 pages. Let's start from here. Yep.
Do both unstable and stable air have dry and...
Yeah, that's actually a good point. So this is completely different thing. That this is surrounding temperature distribution, and then lapse rate is that when you bring the surface air to 1 kilometer altitude, it's 2 different things. So let's start from here. So this green line right here is the 2 thing, kind of a condition that we are going to assume here to improve your understanding or make you confusing. So this is the temperature distribution of the atmosphere. Let's assume this line as temperature distribution of atmosphere. By that means, if you have a thermostat, if you measure the temperature distribution over the altitude, flying, or if you somehow fly to the atmosphere, if you have a thermostat, if you read the temperature in each altitude, you will get this green line, okay? So that's what green line means. And then let's assume you have air mass right here, balloon thing. And then if you bring this air mass to 1 kilometer above, and then if we assume that's completely dry, then temperature decreasing rate is like this, right? So if you bring this thing to 1 kilometer above, then you expect the 10 degrees less temperature, right? So let's compare this thing and that thing right here, okay? So here, so temperature is going to be decreased 10 degrees Celsius, so 20 to 10, right? But surrounding, your temperature is actually lower than air you bring from here to there. Then what's going to be happening? You think it can be rising? No, because it will be rising, right? Because compared with the surrounding, it is hotter, right? Temperature is high, so this is lighter, right? So it's going to keep rising, right? I know it's confusing, but think about it. Again, let me try again.
Well, if the air is colder outside of it, then it'll keep rising until it reaches
Some sort of equilibrium, right? It's neutral, neutral condition, right?
Yeah.
So this is air temperature surrounding. Environmental condition is just like that. And then you have air mass right here. And then if you want to bring this thing up there, then actually temperature of that air mass is actually higher than surrounding. So it's going to keep rising, right? So particle mixing is going to be happening, right? Clear? Yep.
What is the red line?
So red line is basically dry air. So we assume the dry air, right? So this is dry air lapse rate. So basically, if you bring the air mass in this altitude here, bring to this altitude, which is 1 kilometer above, then you expect the temperature of this air mass is going to be 10 degrees less, right? And then if you take a look at the surrounding temperature, the actual observation, then the temperature of the surrounding is actually less than the air you brought from this altitude to here. So it's going to be lighter than surrounding. So it's going to keep rising, okay? And then if you assume the temperature distribution like this in terms of environmental condition, so if you have a thermostat, if you measure the temperature distribution all over the altitude, and then if you get this line, then if you bring this air mass right here to there, the surrounding air actual temperature is significantly higher than your air parcel. So there's no air mixing. It's gonna be happening, right? So that's why we call it stable and unstable. So in this condition, if the temperature distribution is like this, there's no particle mixing. And then if temperature, no, I'm sorry about that. It's completely misleading statement. So if temperature distribution is just like that, then your air mass is going to keep rising. So the particle mixing is going to be happening. That's why we call it unstable condition, right? But stable condition, on the other hand, basically your air mass temperature, if you bring from the ground to 1 kilometer above, and then your air mass is going to have less the colder temperature than surrounding. Basically, there's no particle mixing going on in this scenario. Okay?
It doesn't go down.
What's that? It's going to go down. So basically trapped on the surface. Basically try to go up, but surrounding its temperature is higher, so it's going to be coming back. But if you move a little bit, so let's take a look. Let's consider this kind of scenario. So so polluted air mass is right here, right? So it's just kind of trying to go up a little bit, this much, right? Then what's going to be happening? In this case, surrounding temperature is lower than this temperature. Okay, I can go a little further, and then it will be going up. It will be going up. It will be going up, going up, going up, going up. The kind of thing is happening. So it's going to be particle mixing is going to be happening, right? It's going to keep going up. But if you try to move this air mass, let's assume that's polluted air mass, a little bit toward the little higher altitude side, the temperature surrounding is actually higher than the air mass. So it cannot be going up. It cannot keep going up, so it will just be dropping. So your air pollutant is going to be trapped in the surface layer. Okay? Okay, we'll
So it's stable when surrounding temperatures are hotter?
Yep. your surrounding air is lighter than your air, then the air is going to be sinking, right? So stable so the consequences of this stable condition and unstable condition is that in stable condition, air pollutant is going to be trapped on the ground. So you expect higher concentration of the air pollutants if you have the same emission rate. But unstable air condition, the particle mixing gets more active, so your air pollutant concentration is going to be lower, although air pollutants emission rate is about the same, right? Okay. Show me some smiley face. I'm trying hard right now.
So was the London smog unstable or unstable?
What do you think? So the question is that London type smog is stable condition or unstable condition? That's good.
Stable, but I thought it was.
Really? Why is that?
No, I mean, I understand that it's stable, but like in my reading, I thought it was cold there.
So you think a cold is unstable?
No, I just like, so it was stable.
Uh-huh.
So which means it was warmer there, right?
Why is stable is why you
means that like the surrounding air is colder than the parcel is unstable. So in stable, the surrounding air is warmer than the.
It's all relative sense, right? For example, boiling points of nitrogen is higher than oxygen. Do you know what is the boiling point of the nitrogen? It's like minus 197 Kelvin. And then boiling point of oxygen is like minus 210 or something like that. So both of them is very cold, but it's all relative sense. It's higher or lower, okay? We are talking about, it is warm or warm or cold, not about it. Just temperature differences is higher or lower, right? So it is not, there's no absolute sense of the warm or cold we are talking about. It's all relative sense. Temperature is higher or lower, okay? So let me make this thing a little bit more complicated. I think this is one of the most complicated plot that I will show you for this class. But if you take a look at it, it's not really super complicated. So let's take a look at this red dotted line and then blue dotted line right here. So what's the red dotted line here? So basically, the temperature decrease for 1 kilometer. Altitude range temperature decrease is about 10 degrees Celsius. So what's the red dotted line there? Dry lapse rate, right? So blue line is 6 degrees Celsius. So what's that blue dotted line there? Wet is that's saturated lapse rate, right? 6.5 and then 10. So there's a 2 line here, and then there's a 4 different scenario we assume right here. So one right here, regardless of the humidity of the air right here in 1 kilometer altitude, it's gonna be absolutely unstable because your temperature of the air mass, if you bring this thing up high, then your air mass is actually warmer than surrounding, right? So air mass is gonna keep rising, right? And then let's assume line number 2 here as a surrounding temperature. Then depends on the relative humidity. So it depends on the relative humidity, temperature decrease of this air parcel. If you bring this air parcel to up high, then this is the range of the expected temperature, right? If you have absolutely dry air mass, the temperature change is going to be following this red dotted line. And then if it is absolutely saturated air mass, it's going to be following this blue dotted line, right? So let's assume if it is absolutely absolutely dry, then your surrounding temperature is actually higher than your air parcel, right? Then is it stable or unstable? If it is completely dry. So let's go step by step. Your surrounding temperature is higher than the air mass or lower than the air mass? Higher, right? Surrounding is higher. So is it stable or unstable? So I'm confused. So your temperature is actually, your air mass temperature is lower than surrounding. So is it stable? It's stable, right? Yep, it's stable. So if it is absolutely dry, then it's going to be stable. But on the other hand, if it is absolutely saturated by water, which is temperature decreasing rate of the 6 degrees Celsius, then if you bring this thing little up high, what's going to be happening is that your air mass temperature is actually a little higher than surrounding, so it's unstable, right? So if environmental temperature distribution over the altitude is scenario number 2, depends on the humidity, your stability is going to be determined. So we call it conditionally unstable, or you can call it conditionally stable, right? And then in this regime, then even absolutely saturated air, the temperature is going to be lower than surrounding. Scenario 3 and 4 is going to be absolutely stable. Okay? So this is what they call inversion layer, which is temperature is actually is increasing as you go up high. So this case is a very strong stable layer is formed right here. So there's not going to be any mixing between this layer and the below the surface layer and then up high upper layer of the atmosphere. So all the air pollutant that emitted on the surface is going to be accumulated in the bottom layer, right? That's the consequences of unstable atmosphere. No, stable atmosphere. Man, it's really confusing. Okay. You know what? Let's skip this thing. Don't need to think about it. So this is kind of you can just if you understand everything, you can play with it, but you will be fine if you don't understand this plot at all. So this is green line. Is the environmental temperature distribution. Again, if you measure the temperature from 0 to 3 kilometers above with a thermostat, the temperature distribution is going to be just like this. Let's assume that way. So this red dotted line is dry lapse rate again, and then blue dotted line is the saturated lapse rate, which is 6 degrees Celsius, and then dry lapse rate is 10 degrees Celsius, right? So here on the surface, so basically your air parcel temperature, if you bring this surface air to up high, then higher than surrounding, is by definition unstable, right? So it's going to be keep rising here until you get 0.5 kilometer. So once that air mass on the surface gets 0.5 kilometer, temperature is actually going up, right? So this makes absolutely stable layer right here, right? So the air pollutants from the surface cannot go up to the upper layer right here. So inversion is ending right here. Then depends on the temperature distribution. It can be unsaturated neutral or unstable or even stable condition, depends on the temperature distribution. So this is kind of, if you take a look at this temperature distribution like this, then what you should expect is that basically all the air pollutant is going to be trapped under 0.5 kilometer. Okay? You can understand that far, right? Although, okay. So this is kind of a bottom line thing, right? So usually temperature distribution from the surface about 2 kilometers above looks just like this. On the bottom, about somewhere between 0.5 to 1 kilometer altitude. We call it a mixed layer, usually in the below this inversion layer. Usually the temperature distribution gets unstable condition. So pollution that immediately from the surface mixed pretty well on the bottom. But due to this inversion layer, basically block a mixing between the air above and the surface area. So we usually call it this area the higher altitude region that's separated from the surface by this inversion layer as free troposphere. So free troposphere and surface is separated by this inversion layer. So by definition, inversion layer is temperature is increasing as you go up high. So this is absolutely stable region. Thickness of the this inversion layer is about a few hundred meter. So that actually hinder the mixing of air pollutants from the surface area to free troposphere. Okay? And then depends on that the base height of this inversion layer, so basically determine the mixing height of the surface layer. So if you have lower base height, then you expect more air pollution if there's same amount of emission coming from the surface. Okay? Give me some smiley face. So this is consequences of the those inversion layer, and then kind of the mixing, vertical mixing of the air mass. So this is PBL, means planetary boundary layer. Basically, this is the base height. So within the base height, the mixing, vertical mixing, usually happens 1 or 2 days of time frame. And then because of this inversion layer, which is absolutely stable layer, the mixing got blocked. So it takes a long time. Actually, the air mass out here gets into, the upper layer. We call it free troposphere. So it takes about 1 week actually to the surface air gets into free troposphere. You can just call it higher, the upper layer of the atmosphere. So for the whole troposphere mixing, it takes about 5 months. And then we will discuss about stratosphere a little later, and then I briefly introduced you to stratosphere for the beginning of this quarter. So the stratosphere, the temperature is always increasing as you go up high. So the mixing between stratosphere and then troposphere, it takes about 5 to 10 years. So this is a time frame you need to remember. Maybe I can provide during the exam if I need to discuss about this thing for the exam, just like last midterm. So this is different kind of time scale about the mixing. And then obviously because air pollutants is transported by the air movement, so this basically time frame is going to be determined on the air pollutant transport, and then how those different air pollutants with different lifetime effect on different regions. Okay? Clear? Okay, let's move along. So I probably you guys practice this thing quite a bit. So let's double check that everybody got this stuff. Does exactly the same thing, no trick, nothing. So you have ocean there, you have land there, and then sunny days. Sun is hitting on the surface. Then we talked about this specific heat. So basically specific heat of the water is much, much higher than sand or clay. Then temperature over the ocean is going to be higher or equal or less than land. Only 27, it was 40 something. 20 more seconds. How many of you guys actually responded right now? How many of you guys are not responded? Forgot about bringing the eye clicker. 2, 1, 1. How many of us right in the room? Would you count? So we have 41, 42, 43, okay. I guess that's it. Yeah, still. 7 people.
46.
46. What's the total response? Was 47, so 43. So 46 and 43, I haven't got the 3 responses in this system. How many of you didn't bring iClicker? 1, 2, 3. Okay, we got the math right. So email me if you didn't bring your iClicker. Then you were actually here. So again, let me try again. So because basically this number means that you need more energy to increase the temperature in given weight. So basically this clay and sand, which is basically composition of the land, has far less specific heat than the liquid water. Basically liquid water takes more energy to increase the temperature. So if there's same amount of the energy exerted on the water or the land, the temperature increase of the land is going to be faster than the over the water, right? So temperature over here is going to be higher. So consequences of differential heating in land and sea is the sea breeze. Basically, this air over the land gets lighter, it moves up. So there's some empty space here. Air is moving in, so that makes some circulation in a counterclockwise circulation, right? So let's see. Okay, I'm gonna skip this thing. Probably this is a kind of a preach to the choir or something. So it's the other way around. So during the night, water can retain the heat much efficiently than the land. So temperature over the ocean gets higher than land. The circulation is going to be the other way around, which is clockwise. Okay? That's land, sea breeze, kind of a circulation. And then day and night, that's different direction. Okay? That's all you need to remember. So to understand especially the air pollutant behavior, place like Los Angeles and Orange County, which is very near from the ocean, we need to understand this sea breeze circulation. So we talked about stable and unstable air. Basically, stable air, which is bad for air pollution, right, is caused by actually on the below the surface, air temperature gets lower than the above temperature. Then that makes stable atmosphere, right? If your air temperature on the surface gets lower than up high, basically temperature distribution is going to be no, the other way around. Sorry about that. If your temperature distribution is just like that, temperature and altitude, if your surface temperature T above, let's say, TS, TA, if it is higher, then this is by definition stable layer. So let's discuss about how we can generate this kind of a very stable atmosphere in the natural condition. So one way you can do is that we talked about usually during the night, the temperature above the sea is higher than temperature above the land, right? So somehow this higher temperature of sea surface air is moving into the land, and then it kicking in to the land area, and then if that makes the lower temperature of the surface, then you can make this kind of temperature distribution, which is stable condition. Then if there's air pollution emission is happening on the surface, then the air pollutant is going to be accumulating only on the surface layer. And then the concentration of the air pollutant is going to be higher, right? So that's one way you can do. And then the other way you can do is radiation inversion, we call it. It's kind of the same concept that during the night, your surface lands gets very, very chillier, especially during the winter time. And then once sun came up, then air gets much warmer than the surface. And then you happen to have cold surface air temperature then up high. So especially early morning, you can end up having this kind of temperature distribution that surface temperature gets lower than temperature above. So this is kind of a two-way there's many ways actually you can get this inversion, but this is two most kind of often you can see that stable layer on the surface. Let's go up. So this is more realistic picture of the temperature inversion, how it is happening. So this is what we talked about, marine layer inversion. So basically, cool marine air gets into the land, and then warm air from the land is moved above. Then your temperature just above the surface of the land is going to be lower than temperature above the atmosphere. So you will have this kind of very stable atmospheric temperature distribution, right? So this is 1A. So let's skip the discussion C and B and C situation. Let's take a look at the D. So if you have a deep valley, like here, and then let's read this thing. This is blocking your reading, obviously. So again, that's just we discussed about. In the bottom layer, it gets very cold during the night. And then once sun kind of come up in the early morning, then the air temperature above this valley gets warmer. Then you have very stable layer happens in this valley region. So all the air pollutants that happen in the valley is going to be trapped inside of the valley. So this is two very famous condition that you may often see the air pollution caused by this kind of a very stable layer on the bottom. Okay. My remote is not really working. Here you go. So this is the photo that I already showed you. Then Salt Lake City, you can see the snow on the road. So obviously this is winter time. So this is a nice valley. This is early morning. Then what is this thing? This is nasty air pollution that emitted from this valley, kind of trapped in the valley because of that temperature inversion, which makes this very stable layer. Okay? So once you see this kind of a photo, then you should think about that dry lapse rate, wet lapse rate, and temperature distribution, all sort of things. Now you can do it, right? All right. So let's come back to the Los Angeles area. So let's kind of dissect the Los Angeles area from east to west. Then roughly, it just looks like this way, right? So there's a mountain area, backside of the city. And then this is kind of a flat land. Then we have Pacific Ocean. So there's two kind of actually inversion going on in this situation in Los Angeles. First one is the marine inversion we already discussed about. The relatively chill, cold marine air is kind of invaded into the land, and then that cause inversion over the surface. Another factor is sometimes the hot air mass from inland in that area is moving into our region that actually provide very hot air on top of this cool marine air. So basically, if this is the temperature distribution, what you can expect only marine scenario, then your actual temperature up high in the free troposphere gets much warmer because of this air transport from the very hot desert region. So you will get something like this temperature distribution. And then this is much, much, much stronger, stable air, so that a lot of air pollutant is going to be trapped on the ground boundary layer, okay, in the mixing layer. So this is kind of a snapshot of the daily evolution of the pollution transport in Los Angeles region. So in the early morning, it's in the mid-morning, yeah. Depends on how you define the early morning. If you're early riser, this is mid-morning, or if you wake up like 10 a.m. in the morning, it's going to be early morning, whatsoever. So there's pollution is going to be started emitted in the area, in the city area, and then still the boundary layer, which is mixing layer on the surface, is pretty low because sun is not heating up on the surface that much because this is morning, right? So the concentration of air pollutant gets higher on the surface in the morning. So as day going by, basically the temperature over the surface is rising, which means that there's more convection. So air motion is triggered by the hot surface temperature. Basically, this temperature is moving towards the higher temperature side as the time going by because sun is heating up to the land, and then you expect temperature is going to be changing like this. So your inversion is over. Now you have unstable atmosphere that makes more mixing. But the thing is that if there's a sun out there, the photochemistry is kicking in. So there's strong sea breeze actually move these air pollutants to inland side. And then actually a lot of photochemical reactions, you remember all those arrows, right? That's all triggered by the sun. It's happening in the suburban region. So you expect higher concentration of ozone in suburban area rather than in the city center, right? So what's happening during the night? That actually the breeze is coming from the land to the sea. So during the night, the air mass is going to be moving from the city side over the ocean. But this pollutants over the sea is going to be coming in again during the daytime. Basically, you keep accumulating yesterday's air pollution again to the city during the morning. So it gets worse, worse, worse until it gets rain, which hardly happen in Southern California, right? So this kind of so emission from the car is one thing, and then this kind of weather kind of situation in Los Angeles, and then geographical kind of environments in Los Angeles makes Los Angeles very famous for, which is not good sense for the air pollution, right? So this is kind of keep the Los Angeles smog worse as time going by because some of the residual air pollutants keep rolling in next day. And then usually you expect higher ozone or secondary pollutants concentration in suburban area than city center. So you may think that, well, if I just living in the suburban area, it's going to be everything is going to be nice, clean, and nice. But that's not the case in Southern Californian region. Okay? How much time we have? We have 15 minutes. I think I have enough time. So so far we assume air pollutant temperature is the air mass that has air pollutants temperature is just same as environment, right? But if you assume some tailpipe from the car or the stack in from the factory, usually the emission of air pollutants, the temperature is much higher than environment, right? So tailpipe have you put your hands on the tailpipe or something? No, never do it. It's very hot, the surface. And then if you take all those industrial facility emitting very hot gases that contains air pollutants to the atmosphere. So our starting point is not going to be just like here, which is surface air temperature. It's going to be more like this. It's going to be much hotter, right? So although in this condition, this is inversion layer right here, but if the emission of air pollutants gets much, much hotter than the surrounding, then actually, if you follow this lapse right here, always the surrounding temperature is lower than this lapse rate, then air pollutants that emitted as hot temperature, higher temperature than the surrounding, then actually it will just mix up until it gets here to the atmosphere, right? It's confusing. Should I try? Yep.
So do industries sometimes heat up pollutants in order to get them above?
No, all those industrial processes, basically what they are usually doing is putting a lot of heat to make some reaction, things like that. So usually stack gas or tailpipe from the car has higher temperature than ambient temperature, right? So basically your starting point, if your starting point is just like that, then pollutant is going to be trapped right here, but your air pollutants happen to have higher temperature, which is usually the case. If it is emitted from here, then if you make the line of the dry lapse rate, then you can easily tell then your air pollutant temperature, if you move from here to here, then temperature is actually higher than surrounding, so it's going to be keep going up. So that's one way you can break up that inversion layer. So if your air pollutants get higher temperature, then your mixing actually is going to be much higher than what you expect from this inversion layer. So if you can understand this far, that's great. But if this thing makes you even confused, then forget about this thing, okay? But this thing you need to remember. So this is usually the temperature evolution during the day. So this is 3 a.m. local time, 6 a.m. local time, 9 a.m. local time, noon, and then about 4 p.m. So usually very, very early morning, surface gets much, much cooler because of the all those heat capacity thing. Then surface gets chill up. So usually temperature above the surface is much cooler than temperature above, okay? So basically it just from the surface to all the way up to about 1 kilometer altitude, this temperature inversion is happening right there, right? So this means that this is absolutely stable, then no vertical mixing is going to be going on in this situation. So once sun is started to come up, then sun is going to be heated up the surface, and then surface gets warmer, 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 warmer. Then your mixing height gets higher, 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 and higher, right? So this is kind of evolution of your mixing depth from 6 to about 4 p.m. Once that temperature gets higher, then temperature gets higher, and then your mixing height gets higher, right? So especially winter time, if you travel some city, actually doctors recommend you not to actually make some jogging outside activity, especially early in the morning, because your city's mixing depth is much lower in the early morning. So your air pollutant is going to be accumulated in the surface, and then the concentration gets much higher. So that's the reason that sometimes you don't want to make jogging or the outside activity, especially early in the morning, because all the air pollutant is going to be trapped in the lower atmosphere. Okay? So before we close the discussion about the heating up, things like that, that usually temperature in the city gets much hotter than the temperature around the suburb or the rural area. That is because asphalt on the road, things like that, usually gets much hotter because it has lower heat capacity. So this is kind of a NASA simulation of the temperature distribution over the city. I don't know which city this is, but basically on the road, if you take a look at the place has the pavement, gets much hotter. The red is hotter color. And then some green region like grass field, things like that, gets much cooler. That is because that temperature of the pavement is much higher due to low heat capacity, low specific heat. So, kind of an easy way to you can take a look at this thing is that if you just break your egg on the surface of the a city like Las Vegas, you can easily get the nice egg fries on the even surface. So it gets that hot during the summertime when pavement gets enough heat from the sun during the summertime in some part of the country. So that's the end of the discussion, I think, but I still have 10 minutes. Let me try a few more. So this is photos that actually visualize of the concepts that we discussed so far. So this is about the noon. So you see the mountain back there? You can see clear mixing below this surface. Then all those air pollutants emitted to the atmosphere and then chemically made in the atmosphere, basically trapped below the inversion layer, right? So this is basically your inversion layer height. Late afternoon, you can see the mixing height gets a little bit higher. So if you take a look at this mountain, it got up a little higher, right? So this is basically visualization of this thing. So usually the mixing height, which is from here to here, from base to the ground, it's got max about 4 p.m. So in the late afternoon, you have higher mixing depth, okay? So you can see all those air pollutants below the boundary layer, mixing layer, and then it got trapped there, and then there's not much of mixing between the surface layer and the air above. I have still 5 minutes. I have a very important discussion by end of this class. So this is another thing, and then this is temperature distribution. So what you should take a look is that where this inversion is happening, so basically the air pollutant is gonna be trapped below this base of the inversion. And then if your inversion is stronger, then actually the mixing is gonna be, so if the stronger inversion actually prevent mixing from the surface layer and then above. So the definition of the stronger mixing is that how deep is this inversion layer, and then how much temperature, so temperature differences in this inversion layer. In this case, this is about 6 degrees Celsius. This is only 3 degrees Celsius. So this is much stronger inversion layer, okay? So that's two things you need to remember. So all those things, a nice picture, things like that. So one thing that if you have a very stable atmosphere, if there's some stack there, and then if you have some visual indicators, in this case aerosol soot is coming out from this stack, then usually in stable condition, it's just following the line. In this case, the stack is happened to be right there. Then above the stable condition and then below neutral or unstable condition, then air is going to move the particle is going to move towards to the unstable condition rather than stable, because this stable, we cannot expect this air is actually getting into the stable layer, right? So it's going to be dispersed to the ground, which is unstable region. If it is just unstable, it just makes some random behavior of the particle. So this is the example of the unstable air masses. So I have 5 minutes, and then let me try to explain this thing. So these days we are using a lot of wind energy, right? So that you can see there are a lot of wind farm out there. The giant fan is rotating on top of the mountain kind of thing. So let's discuss about how air pollutants actually can affect that production of wind energy. So air pollutants, if you have air pollutants, particle, things like that, in the sky, then it will prevent solar radiation to get to the surface, right? So what's going to be the consequences of this less solar radiation? You expect lower temperature than without pollution. So let's think about two scenarios. Polluted, not polluted. If there's no this pollution layer, then more solar radiation is going to hit the surface, right? Temperature 1, temperature 2, temperature not polluted, temperature polluted. Then temperature not polluted is going to be a little bit higher than temperature polluted, right? That's very easy guess we can make. And then this is actually some observation of solar radiation actually gets from the surface with or without pollution. So this blue dotted line is the temperature, the solar radiation without pollution. And then this red is the solar radiation with pollution. So this amount of solar radiation gets filtered by the pollution, right? So the less energy obviously will make the lower temperature. So once you have higher energy on the surface, higher temperature on the surface, that means that there's more turbulence and then there's going to be more wind. So this means that the lower temperature due to air pollution, then you expect less wind over the surface. So bless you. So why my thing is not really activating? Here we go. So if we just run the model, then we get the about 7 meter per second of the less wind speed due to air pollution, in this case aerosol. So in the end, we'll get about up to about 10% of their less wind energy due to that air pollutant in the atmosphere, right? So basically we talked about, so far we discussed about how weather is affecting on air pollution, but in this case, that's the other way around, right? Air pollutants actually affecting on the weather, which happens to be wind, and then that is actually affecting on the even wind energy production. Wait, I have 5 more minutes. 2 more minutes. Okay, give me 2 more minutes. So this is actually punchline. This is a lot of fun. So let's take a look at the aerosol again. So you have more aerosol and less aerosol. This is polluted case, and then this is not polluted case. Then Ian discussed about that you need aerosol actually particle to make the cloud, right? So basically, if you have a pollution, then you will have more cloud. If you have a more cloud particle, actually you have less precipitation, less rain. Because basically your cloud particle size is going to be less if you have high aerosol, more cloud particle. But I'm going to discuss about this thing next class.